Good. Today we have a real treat. Very pleased to introduce Kevin Murphy. Kevin is a research scientist and a manager at Google DeepMind, brain at DeepMind. And he's a very long and distinguished history of research. He's the author of a very well-known book, which I'm sure all of you have read and studied, called Probabilistic Machine Learning. He's here to sign the book if you want. He's been previously a professor at UBC for 7 or 8 years, and before that he completed a PhD in UC Berkeley under Stuart Russell. And Kevin is an expert not only on probabilistic machine learning, but also how it relates to many other types of learning, and that's going to be the topic of his talk today. So I'm personally very excited to welcome him here. Let's welcome Kevin.
Great. Thank you for the invitation. It's a great honor to be here at Princeton. I've never been here before, so very excited. So what I wanted to do today is to try to give sort of a big picture view of the field of machine learning from sort of a first principles point of view. Because if you look at the media, like this, machine learning or AI is popping up all the time, right, in many different ways. And it can be hard to try to figure out, like, is there any unifying principles that can tie all these things together. And if you look at arXiv, it's even worse, right? There's just like papers coming out like a fire hose. And it's pretty hard to see the wood for the trees. So as Elad mentioned, I've been writing some books on this topic, and I had to sort of wrap my head around it. Like, how am I going to present all this material? And the game started back in 2012. So I used to be a professor at UBC, and I was teaching machine learning class, and I used the books that are available at the time, primarily Chris Bishop's and the Hasty Tiptroni-Friedman book that some of you may know. But I felt it was inadequate, so I made course notes, and that ended up being my 2012 book. And then I joined Google, and I did other things. And then I thought, well, I probably should refresh my book. It's been a bit of change since 2012. And I kept adding and adding and adding material. And then it got so big, my publisher said, okay, you have to split it into 2. So I now have basically 2 volumes. So the first one's out, it came out last year. It's sort of an introduction to the field. And then the second one, the advanced topics one, will come out this summer. And in the advanced topics one, I sort of take an even broader view and wanted to, I don't capture everything, but I capture many things. And I had to have some framework. So I've now started to calling this framework the 4 pillars of machine learning, which you can sort of view as like a single pillar, which is like decision theory. And then depending on how you parameterize the problem, you end up with different subproblems. And these are not independent, but they're sort of, in a sense, a basis set that span most of the things that people care about. So what I'm gonna do is like walk through these sort of 4 axes or pillars. And then for each one, I'll mention briefly like a little project I've done or am doing in this space. And then I'll conclude. So it's just a series of vignettes, basically, and some glue to try to make it all make sense as a whole. So the high level then is that we're going to talk about sort of one-shot decision-making problems, which are like classic supervised learning problems and prediction problems. Then I'll talk briefly about sequential decision-making, online decision-making, which is related to control theory. And then I'm going to talk, this is the phrase I've come up with. I'm still sort of shopping this framing around, but you can think of it as like decision theory, where the loss function involves measuring what you do with respect to some unknown hidden truth that you never observe, right? And that's how I kind of think about unsupervised learning or discovery. And so you never really know what you're right. And then finally, like the flavor of the month, generative AI. What is that? You can think of that as like a decision-making task where you don't even know what the loss function is. Like, what is the right image you should generate when I type into DALL-E or Imogen, make me a picture of a dog dancing on the moon? I don't know. There's many possible answers, right? So there isn't a well-defined loss function. So so that's sort of the big picture. So interrupt me when you like. Let me just watch the clock. Okay. So I'll start with the foundation. So simple one-shot decision problems. And Elad was asking me just like minutes ago, oh, isn't decision theory frequentist? Well, there's like this frequentist and there's a Bayesian approach, and they have very close connections. I'm just going to present the Bayesian version here. And sorry for the small notation, but I had to do this on the plane. So imagine, this is the setup, right? The sort of generic setup. You're an agent, you get some data X, and you have to pick an action A, and your goal is to minimize your posterior expected loss. So what is the loss you think you will incur if the true state of nature was H, the hidden state? That's defined by some loss function that compares the loss you would incur in state H if you did action A. And you want to minimize that loss. And it's the posterior expectation because you don't know H, so you condition on the data that you do know, and you take averages. Okay, so that's the goal. And obviously the loss function is task dependent, and the hidden states are task dependent, and the actions are task dependent, and so is the data. So they're the knobs that you can change. So H, A, X, and L. And like by wiggling those knobs, you can cover essentially all of machine learning. Okay, but in this abstract formalism, you can see that the optimal thing to do is to pick the action that minimizes the expected loss. That's sort of by definition. Or equivalently, you can maximize expected utility just by flipping signs. And different fields have different conventions, but that's straightforward. Okay, so that's decision theory 101. And what makes it Bayesian is that you condition on the observed data. And if you're a frequentist, you would have a sampling distribution and look at sort of average performance. Okay, so let's make that concrete with a very simple example. So you get some data coming in, maybe it's some image or a piece of text or whatever. And let's suppose the action space is to pick one of C possible class labels. And what is the hidden state of the world? Well, it's the true label that you don't know. And you need a loss function. Well, people often use 0, 1 loss. You get 0 loss if you get the answer correct, if you identify nature's true label, and you get 1 loss otherwise. And in that case, the optimal thing to do is to pick the most probable label, map estimate. Okay, so everyone knows this. It's not always presented this way, but I think this is helpful. What's nice about this framing, I think, is that it's easy to see how you can generalize it. So you might have a belief about the state of the world, but you don't necessarily always have to return your beliefs immediately to the user. There might be other actions you can perform. So the hidden state of the world might be one of C labels, but you might have an action space that says, okay, tell the user it's one of these C labels, or say, I don't know, and refuse to classify because you're not confident enough. And so you can have this often called a reject action. And then you can say, okay, well, I'll define a loss function that says, if, let's parse this thing here. So if the action is to pick the true label, then you get no loss, okay? If the action is to pick an incorrect label, then you're going to incur some error, some loss corresponding to the error. But you can also alternatively pick this reject action, and then you say, I don't know, I'm not going to tell you. And then you'll incur some penalty, lambda r, which is the cost of refusing to classify. And then you can solve that problem. And then basically, if you're sufficiently confident, you predict the answer. Otherwise, you abstain, right? And then by varying these thresholds, you can change the behavior of the algorithm. But this is sort of the key tenet of the Bayesian approach, is that you separate your beliefs about the world from your decisions. So your decisions depend on the relative costs, and your beliefs depend about your modeling assumptions. So that's a nice knob that you have, because these costs might be user dependent, context dependent, and so on. Anyway, you can do, it's not always labeling problems, so you can have vectors that you want to predict, and then often we use L2 loss, and then the optimal thing is the posterior mean, or L1 loss, and then it's the posterior median, and so on and so forth, right? So there's many variations of this that you can create. So, okay, so in general then, what we want to do in this setting is we want to compute our beliefs about the outputs given the inputs, and then compute some summary of that, like the mean or the mode or the median, and that will give us the optimal action. Okay, so we need this predictive distribution, which is the probability of the outputs given the inputs. This is where probability comes in. So Lad said, oh, it's decision theory, it's not probabilistic. Oh, it is, in my worldview. So we want to make predictions about the future for this particular input. And how are we going to do that? Well, we'll assume that we've seen some past examples. So this is where supervised learning comes in. And we'll further assume that we have a parametric model, right, with the parameters theta. So we need to approximate this thing. A simple approximation you can do is just fit the model, like compute a point estimate by computing, say, the map estimate or a regularized estimate of some form, and then plug that parameter in. And then this is called the plug-in approximation. But you could do the full Bayesian thing if you want, but we're mostly just going to take a shortcut and do the more common point estimation. Okay, so then you fit your model, you plug it in, you make predictions, and then you can then plug it into your decision-making rule to, predict the label you believe, or like maybe abstain if you're not confident enough. So this is all quite beautiful, I think. And basically, at the end of the day, we've boiled it down to a standard optimization problem, right? You write a loss, you have a regularizer, and you turn the crank. You throw SGD at it, or some convex solver, or whatever. So where does machine learning come in then? Well, it's really in the model, right? There's going to be lots of kinds of models. There are also questions about the data, but we'll assume that's given to us for now. So in the modeling front, we can have linear models, linear regression and GLMs, and we can have nonlinear models like neural nets, and there are, of course, other kinds of nonlinear models, but this is the flavor of the month. You can do amazing things with these. But like if you step back and you look at the success stories, you might be a skeptic like Yuda Pearl is. He's a well-known professor at UCLA, and he said, oh, this is just glorified curve fitting. Well, maybe. I mean, the thing is, I think it is, in a sense, curve fitting. But when you hear that phrase, you think of something like this on the right. And I think our intuitions in high dimensions are not very good. And the phrase curve fitting is maybe misleading, even if it's technically correct. Because in high dimensional spaces, curve fitting is pretty non-trivial, and you can do amazing things just by fitting high dimensional curves. So as some examples of things that high dimensional curves that I fit in the past often are in the vision domain. So like I think I mentioned, I did a lot of work in computer vision when I first joined Google. So this is some random thing from 2017 where we were learning a mapping from pixels to the poses of people, right? So that's a curve fitting problem, but like the input space is like 1,000,000 dimensional, like 1,000 by 1,000 image, and the output dimension space is a few hundred, because it's the key points of all of the people in the image. And this is pretty useful, right? And this is to some ConvNet kind of thing. And then I've done other work where you're predicting trajectories of players in multiplayer games with some kind of RNN thing. And now this is like bread and butter, right? Everyone does this. I mean, you can just download Keras or PyTorch and do it on your phone. So, but it's kind of amazing how well it works, right? And then you see these headlines saying, oh, now the machines are better than humans and they're going to replace doctors and so on. And so can we all retire? Well, no, not yet, because there are also edge cases. There are a lot of edge cases, and some of them are pretty serious. So this is an example of, I have a Tesla, I love my Tesla, but I don't trust the self-driving enough to turn it on because I might accidentally run over a child or some other horrible edge effect. So there's all of these, skeletons lurking around. And it seems at odds with headlines like this, which make you think that the AI problem is solved, or at least the pattern recognition problem is solved. So what's going on? Well, you can actually sort of distill this problem into a much simpler problem setting. So here's a sort of canonical example that some of you, I'm sure, have seen. Actually, show of hands, who's seen the cow-camel example before? Okay, not that many. All right, so this is hopefully memorable. So these are visually very distinct. So you can train a classifier to distinguish these things, and then you can test it on an image like this, and oftentimes it will fail miserably, even if you take like a pretty high-performing state-of-the-art CNN, and it will call this a camel. Okay, so any guesses why? And don't say if you've already seen this.
The background is yellow.
What's that?
Yeah, the background is, it looks a bit like sand, right? It's a yellow background. And if you look at the training data, lo and behold, like basically all the camels were in the desert and all the cows were on grassy fields. So it just takes a shortcut and it just looks at basically one pixel and it says if it's green, it's cow, if it's yellow, it's camel. And it works on the training data. It gets zero error basically, but it's a fragile artifact of the world, of the data set. And this occurs in many other settings. So this is a slightly more complex example. So in X-ray imagery, you want to do medical diagnosis of various forms. And so these are both patients with some form of pneumonia, but this is a female patient on the left and a male patient on the right. And the model basically it's pretty easy. You can see just by eye, you can do gender classification more easily than you can do pneumonia classification in these images. So basically, if there's any kind of correlation between
gender and disease state, it will just learn to be a gender classifier. And that's actually what happens, because that's a shortcut that might be predictive in the training data, but is not robust. It's an artifact of the training set. So to formalize this, we can go back to our decision theory stuff that we were talking about earlier, or empirical loss. We have some distribution that we train on, and then we're going to minimize the expected loss on the training set. And we just hope that the test set is the same distribution, and if that's true, then life is good. There's a lot of theory that says, okay, with enough data and enough regularization, you can sort of bound the loss. But when the target distribution, PT, is different than the source distribution, PS, then basically all bets are off, right? Because if the world changes in arbitrary ways, well, your loss could be arbitrarily high. Now, obviously, the world doesn't change in arbitrary ways, so we want to characterize what kind of changes can occur and somehow account for that. Okay, so what we would like is some kind of robust optimizer, or one approach is to come up with a robust optimization that tries to minimize the loss with respect to some family of distributions that we might see in the future that are different from what we've seen so far. And how do we characterize that? So an approach that's been taken in the literature that we're going to build on is to say we're going to stratify the population into groups, for example, based on gender or location. And so this is, we'll represent the group by Z or Z, and that's partitioning things. And we're going to assume that the target distribution is the distribution over features and labels. It has these subpopulations, and the subpopulations may change. So that's represented by this lightning bolt. So that's I might train on a predominantly female population and test on a predominantly male population, or vice versa, or train in North America and then deploy in Africa or whatever. But I'm going to assume that the rest of the model is stable under those changes. So the way that the data is generated, if I knew these factors of variation, then the rest of this model is going to be the same, even at test time. So the only thing that's changing is Z. So Z are the things that are unstable, and then you just assume that the rest is stable. And with that setting, if you have access to these Z labels, so you've got ground truth about the partitions, then you can solve this group distributionary robust optimization problem. And that can give you robustness to changes with respect to these wiggles in Z. So this is an approach from some folks at Stanford, and it's very popular and seems to work quite well. But this is like a worst case thing, right? It's a min-max problem, and I'm a Bayesian, and I like to do better than min-max. So if you have data from the test set, you can be adaptive rather than robust. So that's sort of the basic approach that we're taking in this paper that we're working on at the moment, that we hope to submit in a few weeks to NeurIPS. So in the standard paradigm, right, you have an estimator that's fit on your source data. Maybe this is maximum likelihood estimation, and that gives you the source parameters. And then you just plug it in, like I said at the beginning, and you incur some loss on the test set. So what we're going to do is we're going to take our source parameters and we're going to adapt them using the target distribution. So we have unlabeled data from the target distribution that occurs at test time, and then we're going to modify our model a little bit in a way to be described, and then we're going to plug in the modified parameters, and that hopefully will work better because it's got samples from the distribution you're evaluating on. Of course, if they were labeled samples, this would just be supervised fine-tuning, and we know that works really well. But that's super simple. It's effectively I don't want to say it's a solved problem. Olga tells me it doesn't always work. There are still issues even in that setting. I guess it depends on the degree to which the distribution shift. But in the unlabeled setting, it's harder. So what are we going to do? Well, we can write down the posterior over both the labels and these unknown factors using Bayes' rule. And we're going to have a likelihood term, which is the data given the factors times the prior. And we're going to make this causal stability assumption that the generative model is the same, even if I wiggle these factors, right? It's the laws of physics. It's like how images are generated. Maybe the lighting changes, maybe what's in the scene changes, but the way that light creates images is invariant. It's like physics, right? So that's my causal generative model. And then what's changing are like the contents of the scene or the random factors, the lighting or the population or so on. So if I can, so we're going to estimate these two terms. We're going to fit some kind of generative model. And then we're going to also estimate in an unsupervised way the changed prior distribution over the labels and confounding factors. Okay, so that's two parts we have to solve. We're going to estimate these two terms, and then we just plug it into Bayes' rule, and then marginalize out the nuisance factor, and we're done. So step one is, how do we compute this generative model? So if this is an image, what we want is a distribution over images as a function of the label and the nuisance factors. So I'm going to talk later today, I think, about generative models. So this can be done sort of as written, but performance isn't always very good if you try to directly model high-dimensional data. But there's a trick. Because we're only using this model as a classifier, we can just manipulate things with Bayes' rule and rewrite the likelihood as a ratio of two discriminative models. So basically the probability of the labels given the data divided by the prior. So that just, because it's like the likelihood ratio trick, we don't need a generative model. We can just use this ratio of classifiers. So as long as we can fit these two terms, which is going to be very easy, then we're good. So the first thing, the top term is just a standard supervised classifier trained on the source distribution. We're assuming we know Z. That's a strong assumption, and we're working on like a semi-supervised extension of that. But this is similar to DRO, where they assume the group labels are known. And then this is just the unconditional marginals of it characterizes the source population, right? So that you can just estimate by counting. So we're done with part one. That's it. We just take a classifier and an unconditional counting model and rescale. And then for part two, we have to estimate this unknown prior over the labels. Well, you can think of it like a mixture model, and you can just use EM. And in fact, you can show that, I won't go walk you through all these equations, it doesn't really matter, but you can write down the likelihood and you can show it's convex, so EM actually will give you the global optimum. So you could use a different algorithm if you don't like EM, but EM is like super simple and is quite fast. So that's just adapting the shift in the label priors to unknown target distributions. And then we can put two and two together. So what I want is a distribution over the label and the unknown factors. So I plug in my likelihood ratio thing, I plug in my estimated prior from EM, and then that's it. I'm done, that's the method. And the nice thing about this method is, like, I think it's pretty well principled. I mean, it makes a strong assumption about stability, but at least we know what assumption we're making. And it will work on any model. Like, we applied it to decision trees. It'll work on embeddings. A lot of the work in this field is very ad hoc. It's like data augmentation. I'm going to rotate the image and assume that rotations are correlated with the label, and maybe they are. And it'll only work in vision. It doesn't work in language. And so this is like a very generic method.
So Z is like the background in the camel cow thing?
Yes. Okay. Yeah. Or anything what you have access to. So here's a concrete example. So actually, maybe I could have started with this. Like, colored MNIST is like one of the canonical examples in this field. So what you want to do is classify 8s versus 9s, so that's Y. And then Z is the color of the background. So this is sort of spiritually similar to the camel-cow thing. And that's a confounding factor. And the data's been engineered such that they're correlated. So in the training set, most of the 9s are red, and most of the 8s are green. And in the test set, it's switched. So what we can do is we can sweep that correlation factor, and that will give us a range of distributions. So this is a nice test bed because you can like synthetically control the degree of shift between source and target in a very simple way. And that's what the x-axis represents. And then the y-axis is the AUC, area under the ROC curve of our classifier. So higher is better. And then if we train, let's suppose we train where it's like 10% correlation between red and 9s. So 90% between the other condition. So it's trained on a very skewed data set. And then we fit a model, and then if we deploy that model across a range of target distributions, you get the black line. So as the target distribution becomes less and less similar to the source, then performance falls down, a fair amount. I mean, it's still 98%, but this is an easy problem. So, and that's because it latched onto the color as a shortcut, and that's not a stable feature. So we want to improve on that. So you can do the min-max thing, the DRO, and then you'll get basically this flat line, which, as advertised, is robust to changes in the confounding factor. So it's working as expected. But it leaves money on the table if you're in the regime that we're discussing, where you have access to unlabeled target distribution data. And in that case, you can do the adaptive thing. So you turn the EM crank and then you get the blue curve, which is our method. That in the worst case, where things are like 50-50, they're uncorrelated, then you can't beat min-max. But if there is correlation that's different, then you can adapt to it and exploit it. So if there is a change, you observe that and then you use that to help your performance. So that's this is a simple test bed. We tried it on the X-ray data set. Qualitatively, we get the same kind of phenomena. Blue beats orange beats black is the story. Where blue, orange is baseline invariant, and black is like do nothing. Just hope that the world hasn't changed. And this works on pixel classifiers, but you can also, we also did experiments where we had a pre-trained embedding model and then we just did logistic regression. So it's super fast, right? You just adapt the weights. And there's actually a lot of other work on just changing the last layer of a neural network that's similar in spirit. So just to pop up a level, like the big picture here, I think this is a big open problem. Like I think standard supervised learning is more or less solved. But I think this issue of distribution shift is actually very common in the real world. And I think there are interesting open questions about how do you characterize the kinds of shifts that you observe in reality. And the one I talked about doesn't cover all cases, right? So I was talking about changes in the background or like, the gender population. But if you look at some of these other data sets, this is from the Wilds data set at Stanford, you go from satellite imagery of urban areas, let's say in North America to Africa or Asia or something, or you have one cell type to another. So you can see there's some sort of change, but how do we characterize that change? And how do we build that into our models so that we can be robust to those kinds of changes? It's not clear. So I think that's an interesting area to work in. Okay. All right, so I'm going to switch gears now. So that was all like one-shot decision making. So that was actually we're just getting started. But I wanted to point out, even in that basic sandbox, there's still open problems. But now I'm going to talk about sequential decision making and control. So this is a super rich area, very interesting. So I'm not going to be able to go into a lot of detail here because this is too much to cover. But I just wanted to present the highlight, and I'm going to zoom in on one special case. So you can think about the previous setting. We had some state of the world, we got some data, and then we took an action, and then we were done. But now we're going to play that game anytime. So the world's going to evolve according to some state process, and then it's going to spit out data at us, which we observe. These are the X's. And then we're going to build some belief about the world. That's a mental model, B. And then based on our belief state, we're going to take actions, and then we're going to get rewarded or punished by some external critic. So it goes, right? And our goal is to maximize expected reward or maximize expected utility. So this is, it fits into the decision theory framework at the beginning, but now there's an interaction between the decision maker and the world. Okay, so this is super general model class, hard to solve in its most abstract form. So I'm going to dive into a very special case called contextual multi-arm bandits. And this is simplified in three major ways. So first of all, we assume that the world is now fully observed, so we get to see the world state. So it's not partially observed. Secondly, the world just spontaneously enters a state and then moves to the next state without any sort of Markov dependence, and it's independent of our actions. So it just creates data and then creates more data. And what we do is we just see the data and then we react and make a decision and we get a reward. And then another thing arrives. So as a concrete example, like this could be someone shows up at a web page and they type in a search query into Google, and I can't really control what causes that. And then I am the Google advertising system, and I have to decide what ads to show you. And so I create a slate of ads, and then you click on one, hopefully, and make some money for my employer, and you get what you want to see. So, but if all the ads are bad, then you don't click on anything and there's no reward. And so I'm building up a belief about like what kinds of things you're interested in. And therefore I'm building up a belief about the reward function. But the world itself is just like spontaneously throwing data at me. So that's called the multi-arm bandit problem. And why is it called that? I didn't ask, who's heard of bandits before? Okay, so more people know bandits than cow camel. Okay, that's probably good. Yeah, so that's this little octopus. So the one-armed bandit is like a slot machine, and a multi-armed bandit is many slot machines, and you want to know which one you should play, right? So if you think of the actions as being an arm or a machine to play, you've got a finite number of arms potentially, and what makes them contextual is that you see some data and then you decide what arm to pull. So it's just some colorful naming for this model family. You can also have infinite arm bandits, and that's like related to Bayesian optimization. But I won't go into that more. So I mentioned the application to ads and other sort of recommender systems like movie recommendations, but it comes up in health settings and in many other contexts. So this is a very, very widely used model family. Okay. So like one of the core things about this model family and what makes it different than the previous supervised classification regression setting is that the agent controls, the actions it performs affect its beliefs about the world. And if it wants to learn, it might have to perform exploratory actions in order to uncover information. The information isn't just presented passively. It has to sort of probe the world to learn. So you have this fundamental trade-off between exploring new actions or exploiting things that you already know. And so if you know that this restaurant has delicious lunch, but there's this new one, should you go to the new one? Maybe it's crap and then you wasted your lunch on a bad restaurant, right? Or I showed ads to you that you didn't like and you didn't click on anything and I didn't make any money and I could have just shown you more TikTok or something. But maybe there's something better than TikTok, right? So you have to keep exploring if you want to learn about the world. So this is a fundamental problem, and in general, it's like intractable to solve. But there's a lot of heuristics that have been developed, and you can prove properties, optimality properties about some of these heuristics. And a simple one that's very easy to understand and widely used is the upper confidence bound heuristic. And basically it says, for each possible action, predict what the reward you expect to get based on the data that you've seen so far. So your estimate will evolve over time. But you also need some measure of uncertainty because some things you haven't explored a lot. So you need to model your uncertainty. So you're going to have perhaps some standard deviation. You don't have to make Gaussian assumptions, but you can think of this as a Gaussian distribution. And so it's got a mean and a variance, and you want to model that. And then you can make this key assumption called optimism in the face of uncertainty, which is that what you think will happen is you pick the action that maximizes the expected reward plus a sort of exploration bonus. So if you're uncertain, then you say, well, maybe I'll give it a try. And then as your confidence tightens up, then you're going to place your bets on the right thing. But initially, you're going to sort of explore. So this will encourage exploratory behavior. Okay, so this is a standard method. You can also use Thompson sampling that samples from this distribution. And there's like lots of beautiful theory on this. But from a computational point of view, or from a probabilistic modeling point of view, which is sort of my bread and butter, the core problem is how to estimate these distributions of outputs and to update them online, right? So if we assume the model is linear, if we go back to modeling 101, we have a linear model. The reward is just a linear combination of the state vector, and we maybe have a different parameter vector for each action. Then we can do online Bayesian inference for the parameters of this model. And since it's a linear Gaussian model, we can put a Gaussian prior on everything. It's all conjugate and closed form. And then there's a closed form formula that's in page something of my book. And you just turn the Bayesian crank, and it's beautiful and easy to encode, and it's fast, and life is good. But of course, this is assuming the world is linear, which is a very strong assumption. So naturally, people want to use neural nets to solve the same kind of problem. And these are called neural bandits. And now the problem is this is like a nonlinear predictive model, right? But we want to do the same thing, because if we could turn the Bayesian crank, then we can reuse all our existing machinery like UCB and Thompson sampling. So then the open question that we studied is, how do you do efficient online Bayesian inference in neural networks? So this is work we have that we're working on right now. But to set the stage, we're not the first to tackle this problem. So Bayesian inference for neural nets is like a sub-community. And if you want to do it online, this has also been studied. And a natural thing to do is to formulate it as a special kind of dynamical system in which the state represents the parameters of the model that evolve over time. And then you get some observations, and these are conditioned on the actions or the features, right? So you can write down your likelihood model as some nonlinear model, like a Gaussian model with a nonlinear mean. And then you can, let's say that the dynamics of the parameters is actually constant, so they don't change, or they could drift or whatever. You can build in whatever prior you want on the dynamics. And now you've got a nonlinear state space model, and you can open the book, chapter 22 of my book or some other book, and you read about the extend and common filter, which just linearizes the model at every step and does a closed form update and repeats. And this is a beautiful thing, right? So here's an example where we're applying the EKF to fit an MLP as the data streams in. So initially you've seen one data point in orange, sorry, in black, and the mean, it goes through that. But if you sample from your posterior and you ask the model, what do you believe about the worlds? Well, it doesn't really know anything. It makes all kinds of crazy forecasts. But the data is going to stream in bit by bit. And I guess red is the current point, and the black dots are the ones you've seen so far. So it's only seen, half a dozen. It's still pretty uncertain. But we give it, like 20 data points, and it's sort of starting to figure out what's going on with this data. And so the mean is reasonable, and there's uncertainty where there should be uncertainty, arguably. And then, it pretty rapidly settles into the right solution. So this is a very data efficient method for learning about the world. So it's like a perfect fit for our bandit problem and other problems like Bayesian optimization. Okay, so what's the problem? The problem is it takes cubic time in the number of parameters, so it doesn't scale to big models. And that follows just because there's a bunch of matrix inversions that I won't walk you through. So we have two solutions to this problem, one that's published last year and one that we're working on now. So the previous work, we exploited an interesting phenomenon about modern neural networks, which is that they're massively overparameterized. So they might have 1 million parameters, but you only really need like 100 of them. So that's visualized in this figure here. So you can imagine some linear subspace, and you really only need to tell me where you live in that subspace to characterize the model. And you need like the anchor point, the initial condition. And so this was empirically demonstrated in 2018. And then recently there's some theoretical work about why this should hold, because it's not obvious. But this figure, which is from the 2018 paper, just shows you that if you want to say fit the MNIST data set with with an MLP or a CNN, you might typically use a few 100,000 parameters. But in fact, you can get away with this like 700 parameters, and you can reach the same asymptotic performance. And so you need to identify this subspace. So you can actually just use a random subspace, and you can do pretty well. Or you can use a data-driven subspace where you first do a little bit of SGD, and then you look at the trajectory that the parameters evolve in, and then you do principal components on that, and that will give you the subspace, and then you freeze it. So we leverage, this is just a property of many networks. It also depends on the data set, but a lot of modern data sets are very compressible. So we leverage this fact by saying, okay, we're going to compute this subspace, which is represented by the matrix A, and then all we have to do is do Bayesian inference about the location within that subspace. And sort of by construction, that's a low-dimensional vector, so we can afford to do EKF. So we're still cubic, but we're cubic in the subspace. And then it's like, just turn the crank, right? We threw EKF at it, and then once we've got the posterior, we do Thompson sampling, and we plug it into a bandit benchmark, and we win. So the pseudocode is very simple. You compute the subspace based on an initial trajectory, and then you just have this iterative loop where you ask the environment for a state, and then you sample from your posterior, and you pick the maximal action. That's Thompson sampling, and then you do an EKF update, and you repeat.
Why did they kind of believe there's such a subspace? Like, naively, you're just throwing away parameters, right? Like, if you just give a random subspace, it's like just throwing away parameters. Setting a bunch of zero. Like, the null space of A is just zero.
Yeah, I mean, it seems that, the degree, these are not independent, the weights of the neural net are not independent, right? So you want maybe them all to move in the same way, but you're just learning an offset from some random initial condition. If you make this data-driven, it's better. It is more efficient.
So theta star is random in it. It's just...
Yes. It could be random in it, or it could be based on a warm-up SGD. So if you make it data, so the random is sort of the extreme case, and then you might need a much higher dimensional subspace. If you estimate theta star with 10 steps of SGD, then you've anchored it at a pretty good starting point, right? Yeah, and you're in like a good basin of retraction already, right? But I'll come back to that actually. Like, yeah. So you can do random, but like we actually warm up, I think, with 10 samples you get for free, and then the rest you have to choose. The rest you get charged for, basically. Anyway, so you do all that stuff, which is quite simple actually, and it's like 20 lines of code or something, and then you can plug it into various benchmarks. So this is a toy bandits benchmark derived from the MNIST dataset, where the reward is 1 if you predict the label correctly and 0 otherwise. And here's a bunch of plots, and higher is better. And this is 3 model families: a small MLP, a bigger MLP, and a CNN. And the blue bars are our method, which is this subspace EKF. And the green bars are a diagonal approximation where we don't use full covariance, so that's not as good. The red bar is if you do diagonal in the original space without the subspace, so that's very bad actually. This mauve bar is like a linear model, so it's always a good sanity check to try linear as a baseline. And then the orange bars are 2 prior pieces of work. I think one is just being Bayesian about the last layer, the linear layer, and then does point estimation for the nonlinear things. And then there's some extension of that where they jump through hoops to try to learn the feature extractor online as well. But it's a pretty complicated method, but we outperform that as well. And we have results on some other benchmarks, but you get the idea. So just to mention some work in progress. So what the flaw with that, which Jason kind of picked up on, is that there was this sort of warm start phase where we had to specify theta star and A, and then we started doing everything online. And that it kind of feels kind of hokey. And even though people do these games, and more importantly, it's not good if the world's non-stationary, because your subspace might not be optimal. You want to be able to continuously adapt everything. So we're currently working on like a fully online solution that it does Kalman filtering or extended Kalman filtering, but we approximate the posterior precision as diagonal plus low rank. And this actually it turns out to be very closely related to the GGT method that Alav worked on. But this is like a Bayesian spin. But if you make the diagonal low rank assumption, then you can turn the crank and you can use like matrix inversion lemma goodies and like derive very efficiently the new one-step posterior. And you've now expanded your rank from rank L to L plus 1, and then you can just project it back down and then repeat. And you can do it with SVD, or you can use SVD-free methods. And this works quite well. I'm not going to go into detail because it's work in progress, but this is a figure from my student from last night, fresh off the press. This is our method in blue, and this is like error rate over time on fashion MNISTs. And like these are the like 500 data samples, right? So it's super data efficient. And then if you do replay SGD with Adam is in red, replay SGD without Adam is in gray, and online gradient descent without any replay buffer is in green. So we're outperforming all of these things, basically because EKF's a second order optimizer, but we also get uncertainty as well. So we get kind of two goodies. And here's a nice visualization. If you do one pass gradient descent on like the 2 moons data set, that is not very good. And we all know, of course, you can fit the 2 moons data set with a neural network, but in the literature, people are almost always focus on offline learning, and they do many, many sweeps. They just beat it over the head, and then it will submit. But if you just like walk over your data once, it's very bad. But we can walk over the data once, and we're great. So one pass learning, very, very useful, especially when the world changes. And that's sort of my high-level point, just to wrap up this section. Like the world's always changing, and the fields are sort of very much focused on static data sets, and even like ChatGPT is frozen in time, right? It doesn't know anything after 2022. Okay, now they hook it up to Google, so they can keep it fresh. But the base model is actually frozen in time. And that's problematic, I think. So I think online learning should get more attention. Okay. So the last 2 sections will be a little shorter, so I should finish on time. So pivoting yet again. If you look at how statistics is done, they're not usually, I mean, there is some work on prediction, obviously. Control theory and RL doesn't really make its way in statistics very much. A lot of applied statistics is fitting models. Like you have data sets like this, you get like panel data, you measure surveys from different people in different countries and you ask them questions, or you measure drug responses, and you've got pretty low dimensional data, but like there might be heterogeneous effects, and often you're interested in like causal treatment effects. And so you might actually have a meaningful scientific model of your domain, or maybe you just write down sort of a fairly simple hierarchical linear model. And what you're trying to do essentially is understand your data, right? You're not really trying to, you're not doing RL, you're not trying to predict the future. You're just trying to understand the data that you have at hand to gain insight into, nature. So we can think of that as a decision theory problem as well, where like the data, what you condition on is like a set of potentially like labeled data. This is outputs given inputs. And the action space is basically to estimate the parameters of a model. So you choose the model, it means something in your domain. It might be a mechanistic scientific model. And the state of what you're trying to do is estimate nature's parameters, right? You assume nature belongs to your model family, which is a strong assumption, but that's the game you usually play in model-based science. And now you're trying to just fit the model, basically. So we know, right, the optimal estimate is the posterior mean. So how do you compute that? Well, you just do Bayesian parameter estimation, and that's it, you're done, right? So there are like books written on this, right? Lots of long books, Gelman, and I have a few chapters on this topic, but that's sort of the game. So this is what makes this, how this relates to the other parts of the talk is that your loss function here refers to theta star, which is nature's parameter, and you never, ever observe that because it's just a fiction in your head, right? There's no training data. So you can't really tell if you've solved this problem correctly or not, because you never get to see the true parameters. You can plug them in and see if it predicts the future well. But really, whether this model works well or not is like, does it give you insight? And this becomes even more extreme if you have like unlabeled data, which is what machine learning people usually think of when they think about discovery. So now you can imagine you've got like a series of data points, and each data point has a corresponding like hidden vector associated with it, which are like the causal factors of variation. And so for each data point n, you would like to estimate the relevant factors. This might be a compressed representation of your data. So if you have points in 2D, you might assume that there's like some clustering structure, and what you really want to estimate is like, what cluster does my data point belong to? So that's just a number, right? That's z. And how many clusters? Well, 2, 3, I don't know, 20. Nobody knows, right? And there is no truth. There's only utility here. And the utility is like, how close do you get to nature, but you don't really know what nature is. So you need to sort of justify your model by other means, maybe out of sample predictive power. And then once you've convinced someone it's a reasonable model, then conditional on your modeling assumptions, then you just turn the Bayesian crank. And now it's like, how well can you approximate that posterior? And that's actually a difficult subproblem because when you're fitting these models, you've got these latent variables, so you have to marginalize them out. And that's more difficult than the sort of standard supervised learning problem. But there are methods you can use. So I'm going to just do a little deep dive into one such model family, just for fun. There's like tons of papers on this, right? But this is one piece of work I've done in this sort of discovery space. And it's kind of, well, let's see if I can, yeah, let me start with this actually. It's motivated by this video. So I don't know if Ryan Adams was involved with this. Don't think so. Anyway, so Scott Lindemann is a colleague of mine. He's a professor at Stanford in the statistics department. And he does a lot of work on neurobiology where they like track animals in cages and look at their behavior with like video cameras, or in this case, it's a depth camera. And they also stick probes in their brains and simultaneously record from multiple electrodes. And they want to like figure out, can they explain the connection between behavior and neurons, right? Big grand challenge in the neuroscience community. And if you sort of watch this animal for a while, you can just see it has sort of modes of behavior. It might run, it might eat, it might sleep. I think it's just a single animal, so it's not really playing. It might have toys in its cage. So, people can create vocabularies to describe behavior, and we'd like to do that automatically. So, as a simplification of that problem setting, we wanted to start with like just this dot moving around. And if you stare at this long enough, you might be able to see some kind of patterns. I think I flashed, in some senses, the answer already. So I've primed you with visual priming. There's some sort of, this is actually like sweeping out this trajectory. And this is, you could say, okay, one way to explain this behavior is that there's a particle moving according to this trajectory. And this trajectory in turn can be characterized into like simple pieces. Like there's a linear sort of straightaway on the F1 race course, and then there's this curve, and then there's like, maybe 2 other pieces, or maybe there should be 1, it's unclear, and then there's another curve in the opposite direction, right? So there's many ways to explain this. There is sort of, as I said before, there's no truth, there's only like, you might be able to convince people more or less about a reasonable explanation for the data that trades off fidelity with simplicity. So, so you can write down a model that tries to suck that kind of structure out of data. That's the goal. So the X's here are like frames of a video, like the mouse, and we're gonna assume that that data came from a generative process that has 2 kinds of states. So these discrete states that represent sort of behavioral regimes, like eating or sleeping or running. And then there's these continuous variables that represent everything else. So like the pose of the animal and how fast it's moving and all the things that you couldn't explain by only using a single discrete variable. So this is called a hybrid state space model, well-studied model family. These are a beast to fit. They're very difficult. They're very, it's a very natural model family. People have been working on this for decades. But we came up with a method that seems to work pretty well for fitting this. And I won't have time to do all the details, but for the experts in the audience, I can explain the idea in 1 sentence, and the non-experts can zone out. But the trick is, if you have an amortized inference network that conditions on the data and proposes values for the z variables, you can sample from that. And then once the z's are observed, it's like an HMM, right? So you can marginalize out the discrete s's analytically. So you can collapse out all your discrete variables. And now you're left with a reduced model that only has continuous latent variables. And then you can fit it just like a VAE. And then the subroutine, you're doing like forwards, backwards as a subroutine under the hood to compute the marginal likelihood instead of just doing the forwards pass of a neural network. So that's the basic idea. And then you do the usual sort of VAE game. OK, that may have made sense to some of you. If you want to know more, you can ask me. But let me just show you how it works. So this is on that same data. So it receives some sequence of points over time. It was generated, because it's synthetic data, from this model. If we fit this switching nonlinear dynamical system, we recover the truth. You can also fit this kind of data with a switching linear model. So this is prior work. I think it's Chelsea Finn and others. And it also works. But what happens is, since it's a sequence of linear models, it needs more pieces to explain the data. So it oversegments. So there's a trade-off. Like if your nonlinear model is sufficiently rich, then you can actually just get away with a single state, and then it won't switch at all. And if it's too rigid, then it will switch too many times. So there's sort of a balance here. So you want to sort of capture the high-level modes with your discrete variables, and then all the remaining uninteresting variation with your continuous model. So we applied it to some mocap data, and it also discovers some, in this case, it discovers 3 states that correspond to this sort of dancing in place. And then I think this person's going to pivot. And then they dance in place a bit more. And then they pivot again, and so on. So it's got these sort of behavioral motifs that it picks up in an unsupervised way. And we did it on some robotics data. And this is the issue I just mentioned. Because we're using nonlinear, these powerful neural networks, they can sort of overfit, and then it will like collapse to a single mode and say, oh, the whole thing is just one neural net following this nonlinear trajectory. And that's not what we want. So we had to sort of regularize it with some bells and whistles to make it behave the way we want. So these unsupervised discovery methods are difficult in practice. So I think that's still an open research problem to make this sort of robust and turnkey. But we're making progress. So just to pop up, I do think more generally, like there's a lot of potential. I was talking to Tom Griffiths this morning about Bayesian machine learning, and is there any role for it anymore in the era of ChatGPT and so on, and everything's transformers? No, not everything's transformers. Not everything is learning from the internet. Like there's a lot of scientific problems where there isn't a lot of data, and there's a lot of prior knowledge, and machine learning can still be helpful there, where maybe you maybe build a neural net emulator that's faster for like weather forecasting or controlling a particle accelerator or something, or you have a semi black box model, right? So it's got some scientific principles, and you put neural nets in a tasteful way in little pieces, right? So it's not like a black box end to end, but it's still a flexible model. So I think there's a lot to do here. It's difficult, as if you're like a grad student in machine learning, it's hard to work in this space because you can't just like download MNIST, get a result, and publish on arXiv within a week. You actually have to work with domain experts, and you need to rely on them to tell you if you're right or wrong. and you have to publish in a science journal that takes years, right? So the feedback cycle is slower. But ultimately, I think that doesn't mean we shouldn't do it. It's just harder work. Okay, so the last vignette is generative AI, the flavor of the month. It's so popular, like there's a McKinsey article written all about it. I mean, it's everywhere, right? So how do we squeeze this into the decision theoretic point of view? And this is a bit of mental gymnastics. Arguably, it's not a good fit, but you can think of these generative models like ChatGPT as supervised learning. They take a prompt as input X, and they generate text as output Y. That's an X to Y mapping, right? And you give it pairs. It's trained on that. And similarly for the text to image generation stuff that I'll talk about in a minute. So the difference is that it's a one-to-many mapping, right? In supervised learning, we sort of think there's a true answer, and we're trying to recover that true answer, and we use 0-1 loss, right? You're either right or you're wrong. But in these generative AI settings, it's really unclear what the right answer is. If I give you a prompt, let's just do an example. I give you a prompt, a cute corgi lives in a house made of sushi, and it gives you this as the answer. Well, what's the loss function on that? I don't know. Is that good? I think it's pretty good, right? But how you quantify that is really unclear. So I call these like decision-making problems where the loss function itself is ambiguous. So we know the action space is like generate images. We know the state space, it's like the prompts basically. We just don't know what the loss function is. And it's like very subjective. So what do we do in a problem like that? Well, then you can like basically just draw samples from the output and then show the samples to users and maybe use like re-ranking or something as a way to surface the ones to the top, which is kind of like using a loss function actually. So you can learn the loss from human preferences, but the core model might just be a generative model without any sort of decisions being made. Okay, so how do we build these models that like spit out multiple samples? Well, there's tons of models of this form. I call this degenerative modeling zoo. So there's like at least 6 different model families, and each of one of these is a chapter in my book. So I obviously can't go over them all. So I'm just going to mention 2 super briefly. I guess I'm starting with this. Diffusion models is one model family that maps like noise to data. And so the way it works, actually, the intuition is that it's kind of hard to map noise to data, but it's easy to map data to noise, right? We can destroy things quite easily just by corrupting, like blurring the image or adding Gaussian noise. So we can go from left to right. And if you do this sufficiently slowly, you can train a network to undo that process little bit by little bit. And the magic sauce is that this is like a supervised learning problem where you take a noisy image and you just learn it to predict a slightly less noisy version. And you iterate that, and then you can magically go from noise all the way to high quality signals. And you can represent this as a PDE where the gradient is the score function, and you can learn the score function. And there's a lot of interesting mathematics behind this. But that's sort of the high level idea, is that the reason it works, I think, in practice is that it's boiled down to a supervised regression problem, which we know how to solve. And so you just get a lot of data. You can make this noise process conditional on text, and then you can do amazing things like this. It's just phenomenal. So this is some work by colleagues of mine at Google.
So without the text, it's clear it'll work, right? Because it has the right distribution.
Yeah.
But with the text, I don't have any samples from it.
You do. So it's trained with conditional text.
It's trained with text.
Yeah, it's text image pairs. So it's a paired problem. So
I never see the same text twice, so I need a way to I guess there's some way to compute dot products.
Yeah, so the way, do I have a slide on this? Yeah, here's a slide on this. So the way most of these things work, let me just jump to this because I'm out of time. There's tons of papers in this space, right? So we're very active in this space. This is some recent work from some of my colleagues and me. So we take a pre-trained text model that's frozen. So that's learning smoothness in text space. And that's trained on the web. That's like one of these large language models. And then where the image stuff comes in is you learn to basically map noise to image conditional on that text. And you can do that continuous denoising process that I just described. But in this piece of work, we took a different approach where we quantized everything and then treat it like a discrete diffusion process, which has some advantages in terms of speed. And you can do like a side-by-side. So this discrete thing's called Muse. Imogen is the continuous thing that I just mentioned. DALI 2, I think, is some hybrid. Actually, this is from OpenAI. And with the same prompt, they can, each model will generate different answers, and then the different models in turn, have a different look and feel. And it's pretty hard to say what's better, right? It's really a question of taste. But there are sort of other factors beyond quality. There's like, and controllability and speed and so on. And so it's a big design space. So we're sort of building models that populate different parts of that design space for different use cases. And one thing that is found is that bigger models work better. Scale really does help. It's more of the same, so it's not very intellectually interesting, but you can't deny the fact that it's like this is clearly better than this one, right? And this is also true for language models. And why is, there's more knowledge baked into these models, right? So let me just close on text. So obviously ChatGPT, Transformers is the workhorse behind ChatGPT and Bard and all these things. I don't really work much on text models, so I'm not going to go into details, but they're super cool. Everyone knows this, right? They also are very brittle. So this is let me just show this epic fail. This is Andrew Wilson, who I'm meeting tomorrow. He's a professor at NYU, and he just tweeted this like days ago. Like still, as of April 18th, 2023, these models still fall flat on their face in some cases. So the prompt he put in was, the violin can't fit into the box because it's too small. What is too small? And then ChatGPT says, well, here it refers to the violin. The violin is too small to fit into the box, which obviously doesn't make sense. The box is too small for the violin. So this turns out, I asked him actually, this is ChatGPT 3.5, and apparently ChatGPT 4 doesn't have this failure mode because it's bigger, and bigger is better. But like, is this all you need, right? I think this is the $1 million question in machine learning right now is, can we just throw more data, more compute, and more parameters, and will we get to AGI, or do we need something intellectually new? And I don't think anyone knows. I bet on the latter. I don't think scale is all you need. I'm kind of sailing against the wind there a little bit. Anyway, just to wrap up, I have these 4 pillars. There are variations on the decision-making theme. Of course, there are lots of other parts of machine learning I didn't talk about. I call these sort of the foundations under the pillars that are kind of orthogonal to the kind of task you're solving. So all of these problems have something to do with optimization under the hood. So that's like a big field, or posterior inference, Bayesian inference. There's like system stuff that I didn't talk about because I don't really know about it. There's like data things, data privacy, and differential privacy and ethics. And that's obviously a big and important topic that, again, I didn't talk about because it's not my area. So, but I think these high-level pillars, nevertheless, do sort of span most of what's out there. Okay, thank you. Yeah.
So this last part of generative, is there a probabilistic formulation that captures both the data, image generation and language data? It seems like 2 different kind of goals.
Yeah, I mean, the language models, it is a probability model, right? It's a joint distribution over word tokens or word pieces, whatever. So the language model is like, if from a graphical model point of view, they're just autoregressive, right? So it's a fully visible Markov model. The secret sauce is what's the form of P of X given ancestors, and that's what transformer is, right? So all of the action is buried inside of the details of the neural network. But it is a probabilistic generative model. It's quite different to diffusion. The diffusion model actually also uses attention. So like they're not, I mean, these are blocks you can mix and match, right?
I guess I do have more questions.
Yeah.
Thank you again.
Yeah.